project, but we had to do a lot of things which we didn't realize that we had to do. So basically what solar flares are, they are just like a large amount of explosion which happens in the sun. As you know that like sun is a giant dynamic gas giant. So it's not like a different solid. So it's like a dynamic system. So usually you have oscillations in the sun, like in the photosphere, then there's a outer layer of the sun, photosphere, chromosphere and corona. So like these are the layers in which you have like many solar activities. So basically what we wanted to do, analyze the photosphere, because earlier there were papers which analyzed the solar flares on the superficial level, like on the coronal level or on the chromospheric level. But if something is coming as superficial, it had to have something which is like a driving mechanism so that it gets to the upper surfaces. So what we wanted to do, we wanted to analyze the photospheric region, because till now we are able to analyze the photosphere of the sun. Below photosphere we are not able to yet reach through our current observatories. So we analyze the magnetic field and the Doppler velocities. You understand what Doppler velocities are there? So we analyze HMIs, and HMIs are heliomagnetic imager, which is one of the instruments of the Solar Dynamic Observatory. So what is SDO now? Solar Dynamic Observatory is also a type of a satellite which NASA launched. It basically monitors sun. And it has like three instruments. One checks the magnetic field, one checks the Doppler velocity, it checks basically intensity and then gives Doppler velocity of all those things. And the last one is it's like thermal. I don't know the last one because I didn't work on that. It's UV imager. So we are analyzing the kernel size. You will get to know what kernel size are there. So basically let's start. So you guys must have heard of auroras. So northern lights, they are found in south also, southern lights also. So auroras are also known as northern or southern lights. And as you can see, like the first picture you guys must have seen a lot of pictures. But the second one is like how auroras are through space. So I found it like very interesting. And then this is just the theory of how auroras form. Auroras are just, why you don't want to go through all the theory. So there is a video which tells how auroras are formed. Let the video get over there and explain. So as you can see, I have written in this video, there are few significant events which are happening mainly. First, this is, how to pause it, wait 1 minute. Pausing. So this is the eruption of magnetic loops which are there, and now when it crashes with the Earth's magnetic field, as you can see, the major portion, the Earth's magnetic field protects us from the major solar winds which is there. But as you can see, there is the upper portion of the sun, upper portion of the Earth, which is getting traced down. As you can see, the magnetic fields are the solar winds are attacking the Earth, and the magnetic fields protecting the Earth from the middle region. But on the upper region, it is like the solar flares, the solar winds which are there, it traces back to the northern and southern regions. So when these particles which are present in the solar winds, they react with nitrogen and oxygen basically, that releases these kinds of lights. So basically that's why in the only southern regions and in the northern poles, basically you find these auroras. Actually, to be honest, this activity which is there, this activity is basically showing a solar flare happening. I will demonstrate how basically a solar flare is happening, but as you can see the solar flare is happening, it gets detached from the sun, and from the sun it gets traveled through solar winds and it reaches Earth. and when it reaches Earth, as I told you, the magnetosphere of the Earth protects us from basically all the emissions which are there, and the northern and southern poles are mainly affected. And as you will see in the further slides, the magnitude of solar flares affects a lot, because higher the magnitude, the more it has a chance to reach the lower hemisphere, like the equator part of the sun, like lower to the pole, the middle portion of the sun, middle portion of the Earth. And so like now I'm telling you like this is all this auroras thing, like how auroras are happening, and talking about what major activity was there which caused the auroras. Actually, major activities are solar flares, CMEs, which are like coronal mass ejections. Coronal mass ejection is when the sun's when the plasma which is present in the sun gets detached from the sun and like leaves the sun's gravitational field and gets out of the sun's gravitational field, and then it comes towards the it passes on like a solar wind. So that removal, that detachment, then is called the coronal mass ejection, because now it is ejected from the photosphere of the sun. So basically this is like what we were trying to do, what we were trying to analyze. We were trying to analyze the change in the wave properties at the flare kernel sites due to the occurrence of solar flares. I will tell you what kernel sites are there. And as I have told you, sun dynamic system already found the long periodic and short periodic oscillations. Sun dynamic system, I have told you, so there are like oscillations present, which is short and long dynamic oscillations. And so we are here to investigate the response of lower solar atmosphere to the solar flare. As I have told you, in the chromosphere, there were like observations in the chromosphere and the coronal region. But here we are trying to explore the photospheric level of the sun. And we're basically trying to find the impact of the 6 solar flare events. So, as we are a physicist, so when we are exploring some mechanism, we had to have, like, if we have data of the sun, because sun is the nearest star and we have a lot of data of the sun. So we are trying to prove our theory by visualizing many of these flares. We cannot just say that this is the model of a flare by analyzing only one flare and just say, oh, this is the flare model. So when we're investigating some properties of a flare, we have to have like investigate many flare events which can show like what we have expressed like abides by with most of the flare activities which are there. So like this is the literal definition of the solar flare, the solar kernels. So it is a sudden increase in the density of electromagnetic wave producing radiation across the whole domain of the electromagnetic spectrum. It usually occurs in regions where the magnetic field is highly dense and commonly known as active regions. So you guys have heard about active regions in the sun, sunspots and all those regions. And flare kernels are the compact regions in the sun's chromosphere and photosphere. That gives intense emission. So as you can see, this brightening which is there in the photo, this is the main chromosphere region. So these are the main flare kernel sites, because we cannot see corona. There are some powerful coronagraphs which currently they can observe corona, but previously we were not able to observe corona until there was eclipse. In the eclipse, when like the main chromosphere is hidden by the shadow of the moon, so then you can see the outer layer of corona. That was the first time when corona was observed. So basically the solar flare is the coronal phenomena. Even though the main the triggering happens in the lower layers, but flare as a whole is a coronal phenomena. It happens in the corona, and from the chromosphere it emerges, and mainly you can see in the corona. So that brightening which is formed in the chromosphere, that is basically flare kernels. So they are the compact regions in the solar photosphere also, that gives intense emission from the various sides during the flare. So like this is a phase of flare. I don't think like this is necessary, because it's just basically we have characterized the process of flare into 3 different parts, which is initial phase, explosive phase and decay phase. So initial phase is also known as precursor, and this is the the initial phase is not very much observed by the observatories, like the dynamic observatories which are there. Basically, we are able to analyze the flare during the impulsive phase, when the brightening is large, and we have used ground-based telescopes also. But for the sun, we usually prefer the space telescopes because mainly we are investigating sun in the UVs and X-rays, and due to the atmosphere they are not allowed to let in. And radio astronomy is one of the things that using radio telescopes we are able to measure the sun spectrum. But those are only the ground-based telescopes like which we can use to measure the radio wavelengths of the sun. But basically when we are investigating the X-rays in UVs are extreme ultraviolets. We have to go to the space observatories which are there. Abdul is there, Auroras is there. There are 2-3 observatories. So this is all these phases of the flare. So this is the basic CSHKP model, which I was talking about in email also. This kind of seems like a complex system, and it is also a complex system, but the beauty I would say, or like the reality is that this is the worldwide accepted model, but still it satisfies only 50% or not 50% also, 33% or 40% of the total flare which is occurring. Like only those numbers of flares, those proportion of the flares follow this ideal model which we call CSHKP model. The full form is nothing as such. It is the name of scientists. C is from something, Kamiyarkar, Shibata, and all those things. These are the names of the like professors or scientists which made this model. Because initially some scientists said something because he was having less observations. Then few professors came and they were like, okay, but they saw some more observations. So like, okay, we have to keep those, and we added this. So it was like addition of all those scientists' observations was there, and this is the SHKP model. So it is science solar flare model. Its full form, and I written also. As you can see, the full form of this, like the scientist name. What is this? Abdul, all those things. So these. My cursor is visible. No? How can I point to what I am saying? I have to go there. Okay. They are not visible also. So these are the loops, and this is the basic. This is the reconnection. You guys have heard? Because let's leave this. I'll explain using another video which we can show. I think this one is there. You can see this. Wait a minute. This is truly the thing how solar flares occur. This is the reconnection we're talking about, and you see the portion which gets reconnected, and that portion leaves the sun's gravity. And as soon as it leaves the sun's gravity, that is the CME, that is ejected part, coronal mass ejection, that is ejected. So basically, the earlier scientists what they were saying that whenever solar flares happen, they have to have a CME, but many times it does not happen. Even after reconnection, it goes down. So it's basically during a solar flare, there is a chances of coronal mass ejection, but it's not necessary that every time a solar flare happens, they have to have a coronal mass ejection. And this is the artistic way of how the solar flares are occurring. These are the large loops which are forming, and as you can see, these two are combining, and like this reconnection is happening. It is said that during a solar flare, it is equal to the amount of energy which is produced during a solar flare. It is equal to million nuclear bombs exploded simultaneously. The total amount of energy which is produced in a solar flare, if we are able to harbor it, like even if we are able to harbor it like 40 times like 15 or 16%, whole United Nations will not need the supply of electricity, like external source, for the to the whole time span of the whole Earth. That is the true nature of like solar flares. That is the total amount of energy that is like released during solar flares. Again, so these are the now I will simply both of them together. So these are the magnetic fields which are emerging from those dark spots. Those dark spots are the active regions, and those magnetic fields are emerging, and this is the reconnection which happened in the between. Use your reconnection happening in between. there is a reconnection happened, and that portion went off, and this is the loop, and it will again go down, and there is a probability that it might happen that another solar flare is also emerging. So basically, we are not able to tell at the moment that when solar flare is going to happen. We say that during the active regions of you have heard about solar cycles. So during the active regions of the sun, where there is more chance of observing a solar flare. But at the moment, there is no such prediction of solar flares. But we usually see there is a clustering. As I said, there is observability. They are continuously monitoring sun. So they are told that the activities are the sunspots are showing activity in that. So we monitor that patch of the sun through our observatory, and then we investigate through those things. This is again so those two were the artistic representation. So now these two is SDO, Solar Dynamic Observatory. How basically SDO sees it. So the first one is HMI, which I have told you, heliomagnetic imager, and the second one is AIA, that is atmospheric imaging assembly. So this is 1600 angstrom. SDO observes sun in multiple wavelengths, from hundred of wavelengths to thousands of wavelengths, because not every feature is available in every wavelength. So we have investigated these two only, the Doppler velocity and the magnetic field. In the magnetic field, I doubt you will be able to spot any difference. Now the flare has occurred. Nothing. Now you will see this. Now this is very evident here. So during the flare, this is the brightening which is there. This is the intense brightening, and that basically why it's showing in the paths, because we don't usually get a continuous data of that patch. We get images. So basically, the observatories will either give you images of a sun. At the moment, we only get images, or they give you thermal impression. But we were not investigating temperature, so we only needed this intensity and magnetic field. We did not do much about intensity, because intensity is only telling us that at this particular juncture, at this particular instant, solar flare happened. So now we knew that solar flare happened. So now we will use HMI data, the simultaneous thing, and the Doppler data to investigate the velocity and the magnetic field. Now we will take both of them together. I hope so both of them are together. You can see in the HMI also there is some activity which is going on in the main bright portion. So these bright and dark portion are the active regions. So when the magnetic field is coming outside, it's showing white, and when it's coming inside, it's showing dark. So basically, black and white is the polarity difference in the magnetic field which is there. So usually they are very close to each other, or the resolution is that much that is showing close, but usually it's hundreds of kilometer differences. So during solar flares, there is some sharing of those polarities, and due to the sharing, there is probability that magnetic field will get reconnected and solar flare happens. So, as I have already told you that we need data. So this is basically, I have told you from what are the sources of getting data. This is AIA, Atmospheric Imaging Assembly, onward SDO, and it requires a full disk of image of sun up to 1.3 solar radii in 12 UV and UV channels, ultraviolet and extreme ultraviolet. And we have personally used 1600 angstrom of data with the cadence. Cadence means exposure time. 24 seconds हमने एकदम से देखा, and then we took 45 seconds का gap, and then we saw again 24 seconds एकदम पूरे time पे. And L of X means line of sight. Earlier, the previous version of SDO was only able to observe line of sight. Whatever activity is happening, we were only able to tell whether it was happening towards us. But now they upgraded, and now they are able to tell the horizontal velocities also and the vertical velocities also. Now we are also able to get the transverse velocities also. So now we know a lot of things. But basically now we are observing solar flares, so we only needed we we investigated line of sight magnetic field also and line of sight plasma variations or Doppler velocities. Doppler velocities are basically the plasma which is coming outwards from the solar photosphere. But we can see the chromosphere, so it is coming from the photosphere and the chromosphere, all those two regions. There is one thing also, HMI and AIA does not have the same spatial and temporal resolutions. So we have to align those also. So those are technical parts, can leave. So now comes the boring part, what I have done. We investigated, as I have told you, wave properties. What are wave properties? Like there are oscillations already happening in the sun, dynamic oscillations. So we investigated it after solar flares, whether the photosphere, like solar flare happened, it happened. So in the chromosphere, the effect was already found by the previous researchers. We wanted to see the base of the solar, the base of the solar flare which is happening, that is the photosphere, whether it is affected by the occurrence of the solar flare or not, whether the magnetic field and the Doppler velocity which were present in the photosphere, whether they were affected by the occurrence of solar flares or not. So we use FFT's Fourier transform. It usually converts, I don't want to say, time varying into frequency domain. Now what is time domain and frequency domain? When we observe sun, we get the time domain data, like we get the FITs, FITs is like images which we get of the sun. We get those FITs images and all those properties like magnetic field variations and all those velocity variations in the time domain. Time, how it is changing with respect to time. But we were trying to observe the frequency change, so we converted those time domain into frequency domain. So we extracted the main frequencies which are present on those oscillations. So, and wavelength technique is also a similar technique, but FFT has its disadvantages. So, as I said, like, we physicists are never satisfied. We wanted to check like, the results which we are getting from FFT, we are getting the same result from the wavelet or not. So, we applied both of the techniques in the data which we got from the SDO, and we plotted some graphs. So these are the graphs which we got. Is it visible? So this is basically 3 flare kernels. So in one single flare, we observed 4 to 5 different kernel sites. So and we have to investigate 6 to 7 flare kernel sites. So this was the data, this was the graph for 3 flare kernels. The upper one, I don't think so it's visible, right? The upper one is pre-flare. So that is telling what was the oscillations before flare, and the lower one is after flare. So now the lower one is telling what had happened after the flare has occurred. So in this one, in the second row, the last one, you can see there is a dip in the blue line. In the last one, that is mainly telling the occurrence of flares. Solar flares happen. So magnetic field is one of the
What is the y-axis?
I'm telling you. The left side of the y-axis is the magnetic field, and the right side of the magnetic field, the right side of the y-axis is velocity. So in the one graph only, we have plotted magnetic field also, velocity also, because you have to compare how both of them are changing, and that the above one is signal. The first picture is signal. I can zoom it. Can I? Is it visible now? Clearly? So this is the basically one graph which I am showing you. I'll show you the better. This one. So this is the data which we got. This one is the original data which we got from satellite, and this is the data which we used in our calculation. So how we reached from this to this data? Because when we get the data, there are many things. There is noise, there is residuals, and there is a trend in the residual. So what we did, we analyze the trend, we increase the signal to noise ratio, we smooth the graph, and after doing all those things, this is the main signal which we are getting. And this is the signal which we got from the satellite, and this is the signal which we got after processing, which was signal processing. So you can see this is the signal, this is main 0, and this is the signal which we got. And you can see this is the signal which we had. These two are very different. So how we are achieving that signal to the signal which we got is by first applying. We have to see a lot of things. We have to see what kind of trend is there in the data. So we did polynomial fitting. We can do Gaussian fitting also. We can do different types of fitting which helps us analyze that what is the trend of that noise which we get. Usually noise does not have any trend. So we correct the baseline also. So what baseline correction is like, other than the evident features of the graph, we remove everything from the graph. So what we analyze is like, did I press it? Oh. So other than the main evident features, we try to remove everything, because your quality of a graph tells that how good your graph is by removing the noise. So basically, what I have understood by doing one or two not projects, is like one was some winter school and one was project. The main thing is like removing the baseline of the data which we get, and to evidently show what features are there of the evident features are there. As you can see, we have that dip in the graph. So we have to perform those things which can give the dip evidently. So these are all the technical things which we did. It's easy. It's like once you know, all those things are done in Python. So if you if anyone is interested how we got the above data from the data which we got from satellite, you can ask me, I'll tell you. So this graph is like everything which we got, but what do we understood? What we understand from this graph? So this is the main crux which we got after all those signal processing and analyzing all those flares. These are the flares. You can see flare class. So I don't know why they named it. It's like B, C, M, and X. So B class flares are the lowest magnitude class flares. M class, C class is like greater than that. M is 100 times that, and X is 1000 times that. The magnitude, which is the magnitude of the intensity which we observe through the satellites. So X 2.2 tells the magnitude with the when we order something, it's like 2 to the power 3. So X is still that power magnitude 10 to the power 3, and 2.2 is in the what we say, defining what order magnitude is. So 2.2, 1.6, 5.3, 2.7. So these are 6 different flares we analyzed, and after analyzing, what we can see, there is a periodicity. What periodicity is? It's 1 by f. We analyze the frequency as I have told you using Fourier transform, and the frequency which we got, we converted to 1 by f. That is like periodicity or time period. It's same. So this is Doppler data and this is HMI data in minutes. So we analyze average increase. This is the increase in the periodicity. So before flare and after flare, we analyze the Doppler oscillations and HMI oscillations, and we subtracted. Like the increase in the oscillations which we got after solar flares, we subtracted from the initial oscillations which we present before flare. And these magnitudes are the change in the periodicities after the occurrence of flares. So that was the main motive. We wanted to analyze change in the wave properties of the flare kernel size, like whether or not the solar flares affects the photosphere or the already present oscillations or not. So can you see a trend in this periodicity table? HMI mainly, Doppler में तो टाइप नहीं दिख रहा है, but in HMI you can see a trend that as the magnitude of the flare is increasing, the increase in periodicity is also increasing. For the C class it's 3.4, then 5.5, then 7, 8, 9, and for the 2.2 it's 12.240. So the highest is in X2.2. if we observe like more, we are saying this, we are claiming, because general trend of the data, we are saying more the magnitude of the flare, more is the increase in the periodicity which we observe. So that is the main crux which we got after all those analysis, all those things. So we analyzed the property and said, like, now you can measure, now you can observe any flare and you can tell whether the oscillations and the more the magnitude of the flare, more is the change in the wave properties which you can see in the flares. So this is the main crux which we got. Like, this is done. This is what we got after this analysis of the signals which we got. So like it seems satisfactory, but we demanded more, because even after getting all those things, we wanted to check like image. We wanted to get whether the things which we are getting can be represented to the image of the sun. What image means here is, so it's the magnetic field. So these are the images which we are getting from, and you can see after in the first part. The first part is the amplitude plot. So you can see there is an increase in the amplitude. There is increase in the, this is the y-axis. You can see the color variation. So red is the maximum amplitude and the blue one is decrease in amplitude. So first of all, the portion which is showing some color variation, it is showing the change in the it is showing the region where the flare occurred. And those circular blocks which I have shown, it is the main region where flare occurred. So upper one is before flare and lower one is after flare. So you can see there is an increase in the amplitude of the oscillations, which is evident from the image. Is it evident, or I have to zoom? दिख रहा है ना? And as you can see in the pendulum also, you can observe when we increase the amplitude of oscillation, what do we want? That periodicity should decrease, right? जितना amplitude बढ़ाया, the periodicity should decrease, the time period should decrease. So बिल्कुल नहीं दिख रहा है इसमें. This is the main portion which we are observing. This is the frequency which will time period increase करेगा, तो frequency will automatically decrease. So this was the earlier frequency increasing in the, this is which cyan color. This was the frequency which was present earlier before, and after the flare you can see there is a huge gap. So you have seen the frequency decreased a lot. Frequency decreased, amplitude increased, the frequency is decreasing. So now we have shown pictorially, or after doing the spectral analysis, we have shown that it is evident. Basically, this is the sun patch, which the image which I showed you, where we were observing the HMI and the Doppler data. That same patch is this one. We have analyzed the same patch, and we have shown that जहाँ flare occurred हुआ है, only that portion is affected by the that is only affected region in the sun. So the frequencies are decreased, and the periodicity is increased, and the amplitude is also increased, which is like the normal general phenomena. This is the periodicity graph. This is the periodicity, and this is more evident in this was more evident in HMI as compared to Doppler data. Doppler data is also there. Doppler data में इतना evident नहीं है, because I don't know why. This is the Doppler data. You can see there is some increase in the amplitude of the oscillations, but there is no such greater increase. There is such distinctive increase in the amplitude, using which we can say like बहुत ज़्यादा increase हुआ है. So what we are claiming is that we are saying using the data we can assure कि magnetic field is changing. Magnetic field is affected by a large magnitude. But the Doppler data we are not that much sure of what we are observing, what we have observed through our data. So, what is this? Can I press something? What is this? the last slide is only left. So this is the thing. Like, after all those things, what we are, like as I've showed you, like we did the signal processing, we did image analysis. These are all the works of data analysis, right? So how we astrophysicists are different from data analysis, because after getting the data, we have to interpret also. So this is basically the result, and this is a fancy way of which I thought is fancy way. My friends think it's childish way. It's a fancy which I think that it's written data analysis or astrophysics. Let's dig in. It means that we have to analyze the results which we got. We have to analyze what were the basically results. Like amplitude increase हुआ. So what does those amplitude increase means? So basically during a solar flare, the reconnection which is happening is so enormous that the oscillations represented in the photosphere, that is also affected. The solar flare is happening in the corona, and corona के नीचे chromosphere is of few hundreds of kilometers, and उसके नीचे photosphere आता है. We are seeing the magnitude of solar flare is so much that its imprint can still be found in the photosphere. So that's basically what was solar whole project was. So it's an increase in the amplitude also we found, and increase in Doppler velocity also we found, but those Doppler velocity were not that evident in the image form which we showed, but those increase in the amplitude which we could show in the graph, but not the image analysis. But the image analysis showed the HMI increase. So that was the whole project. So thank you. Thank you. Done. You can ask.
Yeah. I mean, I don't really know a lot of this stuff. So can you explain why this reconnection of the magnetic field causes this in this eruption of?
Actually, the energy is already stored in magnetic field. Magnetic field की energy होती है. So when there is reconnection, energy means there some energy which were already stored in the magnetic field, those have to be released. And in the process, there is no one or two lines which are getting reconnected. There are a huge bunch of huge bundles of magnetic field which are getting reconnected. So that magnetic field, when it's reconnected, that energy has to release somewhere. So when there's reconnection is happening, the energy is expulging out. So that is the main thing which we are seeing.
Right. So you're saying that if there's a sun without the solar flare, it will have some sort of bigger loops, and then a smaller loop disconnects, which causes some sort of
smaller loops is not always smaller loop. It's sometimes the portion of the magnetic, upper loop which is there depends on how strong the solar flare is. When it is X-class flare, a large portion gets emitted in the CME form, and we have observed that the X-class flares affects the Earth the maximum as compared to, it's like obvious, the magnitude is greater, it will get affected more. But one thing is more, the amount of energy which we are getting through these solar flares, it is not yet fully explained by the amount of reconnection which is happening. So there are still scientists which are doing the remodeling of the solar flares, because even though the CSHKP's model is able to explain many of the things, but the total amount of energy which we are getting during solar flare is not equal to the amount of energy which we are getting through reconnection. There are many things which are saying micro flares, which is increasing the magnitude, but that is some things which are not as a whole is proven. So reconnection is a major phenomena, but all those energy which we are getting through solar flare is produced by reconnection only. That is not true. That is not yet proven.
It is just the mass ejection, or when it's just the form of energy it is getting sent, right? Not the mass. The mass is actually conserved, right? The energy of sun is not decreasing. The what is called total mass ejection, it doesn't mean
it's mass is ejected.
It does not mean that mass is not constant from us.
Conserved system क्या लेते हो? Like for the applying of conservation of mass or like for conservation of momentum, all those things, angular momentum conserved रहेगा. But the conservation of mass, what is the system? Because we know that the sun will eventually die out in the 5.5 billion years. It has to die out. So it has to die out how? It will emit all those solar activities, which is the core will exhaust, and all those activities which are there on the sun, it will eventually be processed through solar winds, solar flares. The amount of mass will get ejected. So coronal mass ejection means the ejection of mass through the corona of the sun. So mass is ejected. But during solar flare is not coronal mass ejection. In solar flares, there is intense brightening which is there. But whether those brightenings will result in the ejection of the mass, it's not always true. For the ejection of mass, coronal mass ejection has to happen. अगर coronal mass ejection नहीं होगा, तो it might happen that all those reconnection happens. The reconnection is not strong enough to expulge those upper loop outside. Reconnection will happen and it will again go down. The upper portion is not yet detached from the lower loop and it will not be ejected from the corona of the chromosphere of the region of the sun.
It was very nice talk. It was very nice talk. Yeah. So you talked about the loops, right? The ejected loops. So it's a nice question, but why is the shape of the loop, it's constant by the time it reaches, us? So why is it not breaking apart even?
Constant, वो तो pictorial representation है. वो तो it was showing like it is coming through magnetic field and those magnetic field is coming attacking the earth. But basically, as the magnetic field it is all those particles which is getting concentrated in the mass ejection. So all those particles which is ejected from those get bombarded through to the magnetic field. It's not that magnetic fields will get attacked. No, all those particles which it is carrying that whole mass which it is carrying from the detachment of the coronal mass ejection, those particles will hit the earth. It is not the magnetic field which will hit.
So also, since it's a particle phenomenon, the whole thing, how exactly are they escaping the surface of the sun? As such, the escape velocity must be pretty high, right? Mass object like sun. So how exactly are they getting accelerated to reach that stage?
Energy कहाँ से आ रही है? बहुत reconnection से. जब देखो, the plasma में density is very less. Plasma की density we are saying it's like the imagery equations which we use, it assumes that the plasma is fully conductive. There is no, but whenever there is a reconnection, in reconnection there is a squishing of those which is plasma which is there. So it comes. Even though for a plasma, the portion it consistently squeezes the area which is there. So electrons gets hindered. So when it gets hindered, there is a resistance which is causing in between those magnetic lines which is trying to reconnect itself. And during those, if there is resistance causing, there is current in that. V equals to IR. So according to Ohm's law, there will be current sheet which is formed. So I'll show you in the CSHKP model. There is a current sheet which is there. I did explain it. It's not. One minute. I think it should. Is it showing? So this is this portion. This is the main current sheet which is forming because the magnetic fields are trying to compress the plasma which is present in, and it has to get it wants to get out of those restrictions which is imposed by the magnetic field. So it is coming either up or either down. So those down portions with the imprints which we are seeing in the photosphere, those are the plasma which is escaping down, and those plasma which is like emitting up, those are contributing to CMEs. So due to the current heat which is forming, which is due to the hindrance of the electrons, the path of the electron is hindered by the magnetic field. It is constantly trying to stop the electrons from passing, and the time the time at which the electron is not able to pass and there is increase in the resistance in between, that time the current is formed, and when the current is formed there will be like change in potential, all those things which happen in current sheet formation things, and at those times what was the question?
So I was asking how exactly are the particles getting accelerated such that they are able to escape a massive object?
So that's what I think. The field will try to constrict it, and when you have to push it, so it has to get some inflow or outflow. So upper wala, the portion which is getting ejected, which we call outflow, and and the portion which is getting inside, it is getting inflow. क्योंकि magnetic field में plasma रहता है. This is one more thing. In Alfvén flux theorem it says कि Alfvén flux theorem proves it mathematically that the plasma is like trapped in magnetic field. So either we can know the magnetic field, we will tell how plasma is moving, or we can tell how plasma is moving and we can tell magnetic field उसके according होगी. So when the magnetic field is emerging, it is carrying plasma also with itself. So when it's trying to reconnect, the plasma also like colliding with each other. So even though the conductivity is very high, but कुछ electrons होंगे ना. So at the moment when the magnetic field is constantly trying to reconnect, so at very small juncture this current sheet is formed. So on those current sheet, on those small juncture, that is the time when this inflow and outflow is happening. So those inflow gets gets particle accelerated through the sun's inner atmosphere, and the outflow is contributing to the CMEs. And basically we are saying the chromosphere and the photosphere is heating through this only. When the solar flare is happening, the particles just getting inside and it's like moving through chromosphere and photosphere. Those causes chromospheric evaporation, and evaporation is the main region which keeps the chromosphere heating. As you can see, the photospheric temperature is 6,500. But as we are increasing from photosphere to chromosphere, the temperature is increasing. And from chromosphere to corona, it is million kelvins. So one of the main reasons which we say the temperature is varying so much is due to reconnection only. One of the main probable reasons they are saying that due to reconnection, a large amount of energy is releasing, and a large amount of energy releasing causing the heat in that upper layer and the lower chromosphere layers and the coronal layers, which is causing the increase in the mainly what we say the increase in the temperature of these layers. But still the additional increase in the corona, that is like 1.5 million Kelvin, that is not yet being reasoned to build properly with the magnetic field reconnection. Because as I told, the energy which is produced by magnetic field is not enough to give that corona that high temperature. Did I answer your question? That is the main reason. That is the main reason that this inflow and outflow is happening. Because when you construct something, it has to go somewhere. That's the reason. And those particles which is there in the CMEs are those the mid portion of the plasma which is getting trapped in those magnetic field. A magnetic field traps the plasma, and when it gets ejected, it carries all those plasma with it. So it's not magnetic field; it's plasma which will hit the earth. So it's plasma which is magnetic field which holds the plasma inside it, and that will hit the chromosphere. That will hit the magnetosphere of the earth. Done?
The HMI and AI rays, how do they occur scientifically?
What do you mean? HMI is it's the instrument which is present in the XDO, and A is also an instrument. A is atmospheric imaging assembly, which is an instrument. HMI is heliomagnetic imager, which is also an instrument. It's not occurrence. It's observing magnetic field. HMI is observing magnetic field, and AI is observing the velocity of those loops which is present. So what do you mean by how they occur simultaneously? I wanted to show you that whenever there is a flare occurrence, there is obviously change in intensity. Those intensities observed by the EIA, and after we have observed the change in the intensity, we now have the idea that in this region there will be change in magnetic field also. So we take the data from the HMI, observing the magnetic field of those patch, and when others simultaneously, which I was showing that as you can see in HMI there was no visible change in the magnetic field, but in the AIA you can see the intense brightening in the solar flares. So those intensity increase which was distinctive helps us to analyze the solar flare hui hai. And on the left side, the magnetic field which was there, that told us like during solar flare magnetic field is also affected by the flares. So it's the two instruments which checks the whole sun, but one is used for intensity variation, one is used for the magnetic field variation.
Also, about the auroras happening, you said the magnetic field and the
Protect.
solar flares come and then they happen. So how exactly does the coloration comes?
Ah,
Why is it different?
that what I told you. The particles which are traced along the magnetic field of the Earth gets deposited. It's basically hitting the north and southern hemisphere. When these particles are what we say reacting or like providing energy to the nitrogen and oxygen, there will be like change in the wavelengths. And when there is like excitation and excitation will be there will be change the emission of the different wavelengths. So those wavelengths, the color which is emitted through this phenomena, that is mainly causing auroras are there. That's why we see the lightnings are there. And lightnings we can observe in the space also. If any people have shown you. That is the main reason how the color which we are getting in auroras which we are seeing. Huh? Chill out a little bit. Yeah. Take a question now. Choose.
So the main reason the flares are happening is because there is an opposite polarity and they are united.
Main reason is magnetic field density. That is the main reason of the flares happening. And sun is a dynamic system, so obviously there will be an instance when opposite polarity and opposite polarities will come closer, and the magnetic loops which are present far enough will come closer, and then there will be a reconnection there. Because I think reconnection helps in stability of the system. So that they will try to reconnect somehow. And there is not only two active regions which can be connected. Basically, it's like quadruple also. Like four active regions can also come together and form a reconnection can cause a flare. Or three active regions can come closer and form reconnection. Because only like opposite polarity comes and come together. There are different models, pizza cutter model. Every type of model are there for solar flares, which tries to explain how solar flare is happening. That's why it's one of the active research which can say how we can model the solar flare exactly, which we can explain how solar flares are basically happening. So it's basically the reconnection. At the moment, the reconnection which is mainly the reason for the occurrence of solar flares.
I think my question was, then more solar flare activity should be observed around the equator than around the poles.
Why?
Because the sun is rotating around.
Sun differential rotation. तो पोल में किसने बोला?
हाँ, pole पे कम होना चाहिए. क्योंकि वहाँ से mostly magnetic path.
I'm like how I have not talked about the specific region where flare is occurring, right? I have talked about how flare occurs. So it's true, maybe actually it's true like the limb portion of the sun is like less solar activity is happening as compared to the equator region. But sun is very dynamic. Sun में local oscillations भी होते हैं regions में, and sun as a whole also is oscillating. And sun में differential rotation होता है. Outer region होता है that is rotating different from the inner region, and the upper region is rotating different from the equator region also. So it's like lot of different things are happening. So one of the reasons, one of the differential rotation also one of the reasons which cause the reconnection of the reconnection of the magnetic field. Because as you can see, the rotation is there, magnetic fields will get twisted and turns, and those twisting and turning will cause the reconnection to happen. So maybe if flare pole में काम होता है, yes it's true, but I don't have an evidence like poles में ही काम होता है. I have not studied that.
Then what is local oscillation?
Local oscillation is regional oscillation. For example, जब plasma ऊपर आ रहा है या फिर as a whole the sun is like oscillating. But different regions, for example, I talked about the oscillation which is present in the magnetic field. Those are the local oscillations. जो plasma में जो magnetic field है, वो individually को oscillate करते हैं. There will be oscillations in the magnetic field. And as a whole, what I'm talking about the global oscillation is like sun as a whole is also oscillating as a whole. Like different parts are rotating or like not rotating. There's different oscillations, which is a global phenomenon. I think like total around there is a one global oscillation also like time period of sun, and one is like in local oscillations. There is no time period of local oscillation, but global oscillation there are time periods which we have found, and by how they are like very different techniques. Like they use seismology, and which gives how the inner how the waves which are originating from the core of the sun is getting transported through like radiative core, then convection layers, and then is get emitted out. So there are different things. But local oscillation basically means the जो active region है वहाँ पर जो coronal activity हो रही है, not coronal activity, solar activity हो रही है, on those activity का जो oscillation हो रहा है, that is the main so local oscillation talking about.
So how the magnetic field oscillates?
Why like for example अगर magnetic field है तो अगर वो propagate कर रही है तो oscillation तो होगा ना. Oscillation is what, like it's happening continuously, like बन रहा है magnetic field, then is breaking down, then is like forming, then is breaking down, so continuously there will be recorrection happening. It's not basically recorrection, it is like from the inside also it's coming out. So when it is basically it's like when it is moving, a wave is moving, then it's basically oscillation thing ना, move हो रही है तो frequency हमारी frequency आ रही है उस basically wave की. So basically the wave properties change हो रही है. अब किसी लिए तो oscillations की change हो रही है. Oscillation basically the time period which is varying through those waves. So it's just all about oscillation. ऐसा नहीं कि pendulum का rotate कर रही है. It's basically the wave which is having oscillations.